Let's talk about beats. Beats are a phenomenon that happens, it's like interference in time. And it happens when you have two sounds, don't have to be sounds, but that's usually what we're going to look at, two sound waves that have almost the same frequency, but not quite. All right, now in order to understand the phenomenon of beats, it's very, very, very useful to have a trigonometric identity that you probably aren't familiar with because it's been cut out of a lot of the pre-calculus curricula, unfortunately. But whatever. So let's look at these two waves. I've got cosine of 2 pi times 10 times t plus cosine of 2 pi times 12 times t. Now you may be wondering, why did I get this 2 pi there? Why did I choose the 10? What's the significance? Well, let's go ahead and look at what this means. As you know, the period of a sine or a cosine is 2 pi over the coefficient of t. So the coefficient of t is 2 pi times 10. The 2 pi's cancel, and that means that my period is 1/10, and that means that my frequency is, amazingly, 10 hertz. So the frequency here is 12 hertz. So these are almost the same, but they're not exactly the same. So we'll expect this phenomenon of beats. All right, so what is this trigonometric identity that I was mentioning? Well, if I add two cosines together, what I always end up with is 2 times the cosine of the difference of these two things divided by 2. Well, geez, 12 minus 10 is 2. I divide by 2, I get 1, so this is 2 pi t times the cosine of the sum of these two things divided by 2. All right, well, what's that? Well, that's 11, 2 pi times 11t. All right, so who cares? Why is that useful? Well, let's go ahead and look over here at a graph of this function. Now, I don't want to just give you the graph for free. I want to show you how you get it. All right, so I've got 2 times the cosine of 2 pi t times the cosine of 2 pi times 11t. All right, now we know that the frequency of this guy is 1 hertz, and the frequency of this guy is 11 hertz. This guy's oscillating much faster than this guy is. So this guy's just kind of taking his time. He's going to go like that. And this one's going wah, real fast inside, right? So that actually helps us make the graph. In fact, it basically gives us the graph. Because what we're going to say is that during these oscillations, this guy is essentially constant because he's going so slow. So the way we're going to graph this is we're going to pretend that this is a constant. Now we know how to graph 3 times the cosine of something or 5 times the cosine of something, right? We just make little squiggly lines between -3 and +3 or -5 and +5. So here, in order to graph this function, we're going to make little squiggly lines between what? Well, we're going to make them between 2 times the cosine of 2 pi t and -2 times the cosine of 2 pi t. So let's graph 2 times the cosine of 2 pi t. Well, that looks like that. It's a cosine graph. What do you want? And then let's graph -2 times the cosine of 2 pi t. Well, it's going to kind of be the opposite, right? We can do that. Not even hard. All right. So now we need to graph the cosine of 2 pi times 11t between these two green dashed lines. So let's do it. Here we go. We don't get to escape the green lines. So this is the sum of those two sound waves. Notice what we have. We have something that's oscillating at a frequency of 11 hertz. But look what happens. Its amplitude is big and then small, and then big and then small, and then big, and then small, and you can see what happens after that. It just keeps on going back and forth. So the frequency here of this envelope, this green is called the envelope, all right? The frequency was 1 hertz. But within this time period, we got loud twice. This counts as half of a getting loud. This is a whole getting loud, and this is a half of a getting loud. All right? So that means that we're going to get loud 2 times per second. Or at twice the frequency of the envelope. It's 2 times because you're going positive and negative and positive and negative. So it kind of washes out. It doesn't matter whether it's a peak or a trough in this wave. All right? So for that reason, the beat frequency, these are called beats, the beat frequency is always equal to the difference of the 2 frequencies. So here I had 12 and 10. My beat frequency is the absolute value of 12 minus 10 hertz, or 2 hertz. I'll expect it to get loud 2 times per second. All right, so let's see how a problem would be solved using this technique. So this is a sample problem that I've seen on, some of these state tests. A tuning fork with a frequency of 440 hertz, that's middle A, that's the proper frequency for middle A, is played along with the middle A string of a violin, and 2 beats per second are heard. What are the possible frequencies of the A string on the violin? Well, if 2 beats per second are heard, then that means that the difference between the violin string's frequency and the tuning fork's frequency must be 2 hertz. Now, it doesn't tell us whether it's bigger or smaller. It just tells us that the difference is 2. So there's 2 answers, 438 hertz or 442 hertz. Not a difficult problem at all, but you do have to know what to do. This whole idea of beats is extremely important in musical instruments. I've often asked classes, have you ever heard this before? And I've had lots of students, oh yeah, I've heard it before. What does it mean? It means you're out of tune. That's how you tune a musical instrument. You play your note along with the proper note and you listen for beats. The thing is that it's much easier to hear beats loud, soft, loud, soft, loud, soft than it is to tell the difference between 438 hertz and 440 hertz if you just hear them separately, right? You got to have perfect pitch to tell the difference between those 2 things. But if you hear them together, you hear beats or you don't. Pretty obvious. Another important phenomenon that uses this, or maybe it's not a phenomenon, maybe it's kind of an unfortunate state of affairs, is radar guns. They use exactly this. So they'll shoot a laser beam off your car and then it comes back. And because you're moving, the frequency that comes back is different from the frequency that they sent out. It's not very much different, but it's a little bit different. And so then they look at the beats, they use that to measure how fast you were going, and then they pull you over. All right, that's beats.